Hi, in Hong Kong, one of the most popular drink is the iced lemon tea, as you can see on my screen here. And so when I drank the iced lemon tea, I start to think of a physics question. The question is that when you have the ice water reaching the top of your cup, barely overflowing, you could actually do an experiment to see it. And how you can do it is simply get ice and the water with a cup. You can firstly fill up the glass with most of them as water, maybe up to this level if you like to, and then start to add the ice cube into it, and of course the water level, according to simply Archimedes principle, the water level would increase. You can keep adding the ice until the water level would overflow, or you can add water, or it doesn't really matter. So try to add until tiny bit of water overflow. So you can see this must be at the critical point where the cup cannot take any more water or any more ice. And so this is the initial point of your experiment. And my question once again is, maybe after the ice are melted or they are melting, what will happen to the water? There are only three options. One is the water will overflow like we did when you prepare initially, or the water level actually will get lower after the ice are melted. B is there's no change, basically no change in the water level. So what do you think? Please pause the video and think about it. You can either think of using some sort of formula to prove it, or you can use the experiment approach to do it. I also created a poll on this website, so you can go there. I'll put the link in the description below. You can choose your answer and click the vote button. You can then also see other people's votes as well. So please do it now and pause the video.
A few moments later.
Alright, so let's take a look at this video first. So you can see this guy is adding the ice, and I think he's adding more and more. Yeah, you can see just now the water kind of drip, just a tiny bit. So it should be, again, it should be at the critical amount that the cup cannot take any more of water. So let's see. You also see a fact that the ice are actually extended from the top level of the cup. So that means it actually occupies more space than you can have within the cup. And I think the ice are melting, and there isn't anything that happened so far. It's all clean and dry. However, I don't like the way that the video is not like taken in a time lapse. So I think it's better if it can be done in one video. Okay, so you can kind of see the ice are basically all melted. And some of you may be thinking of the water surface tension. And so if you look at the water level right here, you don't even see the curvature of the water level. So the answer is actually no change in water level. Alright, so just now that one was the experiment approach. As a physicist, we would like to also derive in the theoretical approach as well. So I would like you to show me how you can derive the formula to show that there's no water level change. So pause the video, try it now, and remember the answer is no change. How you can show it in formula. Do it now.
2,000 years later.
There might be different ways of deriving it, but I'll show you mine first. So if yours is different from mine, please let me know in the comment section below. So first of all, we'll need to define variables so that we can present and communicate easily. So let me define Mi is the mass of the ice, M W to be the mass of the water. And so for the water, it will think of the cup originally, it has a certain level, so this will be the volume of the water. At the same time, for all the ice cube that you add in, they will also have a volume as well, so I'll use VI to represent them. At the same time, you can see that the ice are actually kind of, again, like I said, extending from the cup itself. So that's something to do with the density of the ice is less than the water itself. So that's why we will find out if this is a cup of water, then actually I can use the same diagram. So again, here you have a missing volume here, which hopefully is the volume of the melted ice. Okay, I hope you understand what I mean. So our objective is hopefully find out the missing volume, which is the empty space here, because we want to prove that there's no change, right? That means the missing part of the cup before you add the ice should equals to the volume of the melted ice. Okay, that means it's water, of course. Melted ice means water. So those ice, when they melt to become water, if the volume of those equal to the volume of missing, then it should explain the water level remain the same. There are two very fundamental physics law you need in this approach. First is the Archimedes principle, or you can also derive it into the buoyancy force. So let me just use buoyancy force. Buoyancy force is defined as rho Vg, and so for the F here, the force is actually the force of the weight of the ice acting onto the water. So I will put Wi here, ice weight, and for the rho, it is density of the medium of the liquid that you are having. So that will be for the water, and for the volume, and that will be the displaced volume. Be careful. So that means that should be the missing, because this is how much water we got displaced, right? Because when we start this experiment, we keep adding the ice so that it will reach the top only. So this is the missing. Oh, a bit too long. Let's just put M. Okay, so for the G is simply the gravity of the Earth. And so if you further derive this, of course you should know the weight is equal to mg. So mass of the ice times g. And I'll just copy this. And so the g will cancel out, and you get mass of the ice equal to density of the water times the missing volume. Secondly, what you may think of is the formula of density definition. So rho equals to m over v in general. If you don't know how this is useful, just try to abuse it by applying on all the things that you have here. So I can apply it onto the ice, which will equal to mass of the ice over volume of the ice. Be careful that the volume of the ice does not equal to the missing volume, because again the ice is extending outside from the cup, so it should be slightly bigger. We could also apply the density onto the water in the cup originally, so that will be mass of the water over volume of the water. We could also apply this equation to the melted ice. Melted ice, of course, they are water, and so the density we should use should be of the water. But then for the mass, we can then use the mass of the ice, and so for their volume would then be the volume of the melted ice. Okay, so for now you probably already see the answer. We have got one equation here and another equation here. Remember, they are from different fundamentals law. One is from the Archimedes principle, which is the buoyancy force. The other one is from the density. However, they have got a very similar term. One is mi, the other one is rho w. So let me just rearrange this one so that we can have, let me just copy this first. Okay, remember the Vm is missing volume. And so if we rearrange this, then we can have rho w times V melt, alright, melted ice volume. And so obviously when you try to look at these two equations, then disregard this one now. Let's forget about this now. Then you can further cancel out this, and that means you have then find out V melted, the melted ice volume is the missing space, the space here, alright, the volume of this. So that's why at the end you will find out the water level is exactly the same. Hey, please don't close the video yet. I will still want to ask you two more questions actually. The first question is, can you spot any kind of assumptions in our proof here so that this can be valid? I could think of two very important assumptions. So I want you to pause the video, think about it, see if you can think of that two assumptions.
A few moments later.
Alright, first assumption is actually evaporation. However, this assumption is not really essential because even if there's evaporation, the rate is rather small. So it shouldn't be very noticeable in affecting our result. Number two is actually having the ice and water, that means from the beginning to be pure water. Okay, and if one of them is seawater, maybe, just maybe, the result will be different. We'll come back to talk about the effect of the seawater or salty water in this situation. But then the second question I would like you to think about it first is, why is this question, alright, about the overflowing of the water important to us, to our world? I mean, I don't just simply ask you this for fun only. Of course this is fun, and it's not only about lemon tea or any iced tea. It's really about our world. So can you relate that to our world? I'll give you a few seconds. This question is actually very important because it's related to our Earth. As you know, global warming, climate change has been a big issue for all of us, and one of the consequences of global warming is that the water level of the sea will increase over the years, and if we don't stop this trend, then some cities near the coastline of the sea, then it would simply be submerged by the water eventually after maybe 10 or 20 years. And so the thing that I think we should identify is what is actually the cause of this increase of water level. There is actually a concept that people usually overlook when you were young, is that there's a difference between glacier and iceberg. The difference between these two is that iceberg, if you have watched Titanic, you know this is simply a piece of big ice that is on top of the sea, that's floating. So just like the ice of your lemon tea, alright, floating on top of the water. Meanwhile, the glacier is some sort of, well, it could be a composition of snow or ice, but the most important thing is it is landed on top of the mountain. So it's not floating on the water, but they supported by the land. And that actually makes a big difference. Because for iceberg, as we said in the question, it is a piece of ice simply floating on top of the water. And it actually doesn't change the water level according to what we just derived. And so that means next time when you watch those NGO video asking you for donation, if they're showing you an iceberg that is melting, then it is actually not scientific, because the water level shouldn't be changing when the iceberg melt, because it's already in the water. However, for glacier, because it's on the land, so its volume is not actually being accounted to the sea. Only when the ice or snow or whatsoever got melted and become water, and of course water will flow and go to the lower level, and so that will go into the sea, and eventually, just like when you simply release the ice onto the ice lemon tea, then the water level will increase certainly. And so that will be the main issue, and that's why if you are the scientist that taking care of, I mean, we all should be taking care, but if you are the one that trying to evaluate the how serious the climate change will be in terms of the sea level change, then you should be looking at the iceberg. No, you should be looking at the glacier instead of the iceberg. However, if you are a bit more skeptical about what I said, which you should, then you can go to Google and try to research more relevant information. Here is one piece of article that I find from the National Snow and Ice Data Center, which the name sounds very promising. And there's a professor from the St. Mary's University, Department of Astronomy and Physics, saying that the melting of the floating ice, which is the one that we said, would actually raise the sea level. So who is right then? The argument from this professor is saying that it is different from having fresh water and freshwater ice, because what we did just now, like I said in assumption number 2, is saying that when the ice are melted, it turns into water, and in our calculation, not in our derived work, the density of the melted ice, which is water, is the same as the density of the water inside the cup originally. But then in the nature, when the iceberg melts, it is onto the sea, which is salty water, and so therefore the density will be different, because for iceberg, most of the iceberg are composite with the pure water, so the density is actually different. So shall we revisit our equation and see how that will make a change? Let's just revisit all the things that we wrote earlier. So we still want to find out whether or not the missing volume, so again the missing part, is the same as the volume of the melted ice. So if it is not, if somehow this is bigger or smaller, then that means your answer will be different. So let's start with Archimedes' principle again. So this time, since we are having the iceberg, which is pure water ice, floating on the sea water, then the rho here would then be changed, right? This one would now be the sea water, and so for sea water, because it has mineral, it has NaCl, so it will be greater, and that is why when you have any kind of substance on the sea, it's much easier to flow. So if this increase, okay, sea water SW, then this is the change for the equation here. And then maybe it's better to call this not the missing volume, but then the displaced volume that originally displaced by the iceberg itself. And when we look at the second equation that we use, which is the density again, the rho W is still the same, because like I said, the iceberg is made of pure water. So when they melt, it is of the density of pure water, of course. And then mass of the ice unchanged, V melt is simply just a definition. So that means at the end, we can only relate it with Mi. Okay, we can still do Mi like we did, but then now the difference is for this one, yeah, this part is still fine, but then for this part is now SW and the displaced volume. And so what you can see is that if this is the case, then we can rearrange these two parts of the formula, as in the V melt over V displaced equals to rho SW over rho W. Okay, and so since once again rho SW seawater has a greater density than the pure water itself, and so that means this fraction must be greater than 1. And that means by looking at this, then the V melt must be greater than V displaced. So that, I think that is why in the experiment, I mean that professor did experiment finding out the melted, after the ice are melted in the seawater, the level actually increase. This is why, because you have actually more volume when you melt than you have displaced originally. So I guess we still have to care the iceberg if they melt, but then the amount would not be as much, because when the iceberg melted, the water level will be increased by the ratio of the sea water density over the pure water density, which is not a lot, which is very tiny. From the professor's experiment, he found out that it will increase by about 2.6% of the volume that you originally have. So that's why in his experiment, it will be increasing for about 4 centimeters. I don't know the parameters, but then there must be an increase. And this increase, probably you can compare that with the ratio I just talked about, right? They should match. And so now I think we should revisit the idea of iceberg, right? So now, since iceberg really is probably floating on the sea, so that means it would really increase it. However, still, when you compare that to glacier, glacier is much more worse, because when you have a big chunk of ice from the glacier drop into the sea, and that's it. That is the big increase. All right, talking about iceberg, which has already originally displaced the seawater already, that 2.6%, yes, is of course accountable, but then it's not a lot comparing to how effective it is, or serious it is when the ice from the glacier drop into the sea. I hope you enjoy learning with me in this video. If you do so, please hit the like button and subscribe to my channel. If you also think that the planet is very important for us and also our next generation, spread and share this video to your family and friends. I'll see you again next time.